first of many exciting tasks that we have this year in MediaEval. Then this in particular is the no audio multimodal speak detection one. My name is Laura. So this task in particular focuses on detecting speaking status in this kind of scenes. So they are crowded, there are people mingling. So you can think of it seems like a cocktail party, like a poster session, etc., etc. So there are a different approach when it comes to detecting who is speaking or not because of the wildness of it. And we have to come up with really clever solutions on how to do this, especially automatically. And here's when machine learning comes into the picture, because detecting the speaking status is one of the main components in order to further analyze these scenarios for social behavior analysis, for group activity, and all these kind of really exciting problems. So the issue with this task in particular is that for this kind of events, just going to the people and like give them a microphone and record what they're saying, it can be perceived, or mostly be perceived, as really private invasive. And in one particular case where this data set come along, for example, this was a speed date session when the people were actually being recorded while having a date with someone, like these 3 minutes. So I already see a bunch of faces cringing, which is obviously people don't like to be recorded directly when they're trying to lure someone. So for this kind of cases, speaking directly from audio is a no-no. So how do we tackle that? How do we still try to detect speaking, or who is speaking in a group, which is a really important cue for other activities, without actually recording them? And that's what this the problem of this task was about. So to leverage that, we rely on this assumption, or at least something that has been proven in social science. When we speak, we move more. You can see this, well, you can see right now in myself, I'm moving all over. But you can see here clearly that when she speaks, she also, her body movement is more than when she's actually listening. So the idea of the task is, okay, we can leverage that. We can give to the participants, instead of a microphone like this one that I have right now in my face, we can give them a wearable accelerometer that is going to record how they move, or how the movement that they make in triaxial, and then we can also record them from top view, from video. The top view part is also so it's not intrusive, really intrusive. So doing this has several challenges that we already announced to the participants, and I'm pretty sure the participants got it when they were doing their work. Basically, people move differently depending on the personality type that you have. For example, you can be more expressive or really not that expressive, but at the end, the sentiment you are trying to convey is basically the same. So an example is here in the slides. You can see both of them, they are doing the exact same gesture, which is basically counting. One is really quiet doing so, and the other one is really expressive. Since we're recording all this data in the wild, you don't have control scenario to when you're recording the video. You have changing light conditions, you have shadows all over the place. People, they get really close to each other when they cannot hear, for example, and they try to hear closer. So you have overlapping windows. So you have all this noisy issue data that comes along with the task as well. So in particular, what we were given to the participants this year was part of the match and mingle dataset. That is a dataset that is openly available if anyone wants to use it for something additional to the speak detection. But for particularly this task, we give the participants the recordings from the video and the wearable, and we give them manual annotations for the speaking status. There's also another different kind of manual annotations if you want to just quickly go and look for for the dataset for the future. Also, a lot of questionnaires. Really cool dataset. I'm proud of it. So in the part of the wearable, all the participants have device that was hanging like one of these. So the base idea is just simulate one of these, but with the wearable in it. So we can have all the acceleration. We have 22 minutes of data recording at 20 hertz for that. For the videos, we have the big videos, but we already help the participants by cropping only to each different subject, because we also have multiple cameras. So if one person goes from one camera to the other, it's a little bit tricky. So we already did that work for them, and they just give them per participant a video. Again, 22 minutes, 20 frames per second. And then we give them the manual annotations for speaking, binary binary annotation. So it's basically speaking, no speaking for all the participants, 20 frames per second. So there were two main subtasks. One, it was what we call the unimodal subtask, which basically was try to detect only if a person is speaking, yes or no, only from the accelerometer and only from the video separately. And then it was the multimodal subtask, which is try a way to fuse these two. So you have already your unimodal, video, and accelerometer. Try to fuse the predictions of those. For this important note, for this representation, I put it as a late fusion, meaning the fusion was done afterwards, but the participants were already also encouraged, or they could do the fusion in an early way. So concatenate the features instead of the decision. For the evaluation, we try to follow the good practices that I've been told I missed yesterday for the bingo. So we really separate subjects between the training and the testing. So the participants have 54 subjects for the training, and then were later, after they were already completing some tasks, they were given 16 completely different ones for the test sets. This is to do a subject-independent kind of analysis. If they wanted to do a subject-specific, they also were given an additional proportion of the participants that they already had. They were separated by time. You can see here, it was the 22 minutes they were given. And then we separated, we left about 3 minutes of separation in time for the actual test set. So there was no overlap in time, temporal overlap. So this year's, how much time do we have? Okay. This year we have 3 submissions. 2 of them are here today, and they're going to present next to me. I'm just gonna be really quickly presenting what Lian Dong and everyone did for that. Just a quick summary. This year, again, only we received subject independent results. So it will be really nice to see subject specific, but that's an extra work, so we get it. Again, we get only late fusion combinations for the multimodal task. And it seems that this year, the main source of trouble for the participants were the changes in appearances in video. They all reported their issues when they were dealing with that. So really quickly, I'm going to present Lian Dong's and company presentation. They couldn't be here, sadly, but they did send us everything, the working notes and the presentation. I did have to squish the presentations a little bit to make it fit to MediaEval format, so I apologize for the authors if it changed a little bit, but basically that's it. They presented the paper called Combining Both Body Pose and Movement Modality for No Audio Speak Detection, which was really nice to see people trying to do body pose and body movement in the video. So you can see here an example of what they did. So from the video, for each one of them, they estimated the pose of the people. And the hypothesis basically was that from that and how that move, they can detect the speaker. And they also did some sequential classification using a logistic regression and one-com filter. So you can see here, there is more in the actual working notes. So how they did this. This apply this regional multi-person post-estimation model that they also propose. And they apply it basically to all the participants, as I said. But sadly, they encounter some issues when they come to the results. They found that, well, overall, the accelerometer gives the best performance overall. Mainly, and we assume because that is just really subject specific. But as you can see, the video started to have its issues. And the analysis, they reported that basically it was because the post-estimator was not working well all the time. Basically because in the video, people change appearance a lot. Depending on how they are with respect with the camera, that their appearances change, and that tends to affect the post-estimator. So lessons for the future, for all the from all the submissions that we have, the task is still challenging, but it was really nice to see that people were working on it. We just needed to find them. So something that we found out as in the logistic size while doing the broadcast about the task is not only did we did the broadcast overall, but we actually tried to find groups that were working in similar things as we are working, so similar to this task. And by doing that and really targeting people that might be interesting given their work sort of overlap, we got additional submissions, which that was a really cool thing for us to see. We then, I guess, for next year's, it will be how to compensate for these differences in appearance. Really something that either us as organizers, we have to address, or really move into that direction maybe from the part of the video. And this year we added also a baseline in both modalities, video and wearable, and that seemed to speed up the process this year. So thank you, and if you have any questions, and once again, promoting the dataset, that's it.